All right, part two of our review, after we did the math, starting down here with waves, we're going to put the order of electromagnetic waves in longest to shortest, highest to lowest, least to most. All right, so before you even start thinking about that, the first thing that we probably want to do is just to put the electromagnetic waves in order. I tried to help out with giving us a memory device for that with Marvin the Martians. So the memory device was raging, Martians invaded Venus using X-ray guns. And so those letters should help us to remember the first letter of each of the types of electromagnetic waves. R for radio, M for microwave, I for infrared, V for visible, U for ultraviolet, X for X-rays, and G for gamma. Now, I want to hop down here in just a second and do this right now and go ahead and do the colors as well, because the colors are the parts of the visible light, and the memory device for that is the fictional name of Roy G. Biv for red, orange, yellow, green, blue, indigo, and violet. Now, again, this is our visible, and you'll notice that red light is the beginning of the visible light, and it's right next to infrared. So infrared has the word red in it. At the other end of the visible spectrum is the U, which is for ultraviolet. Ultraviolet is next to violet. If you get these written out this way, that's kind of half the battle, because the answer is either from left to right or from right to left, right? So as you go through and do these, radio waves to gamma. So at this end down here, radio waves are really long. And the other thing about long waves is they don't have as much energy because they're just not coming by very often because they are so long. Now, again, another reminder, these all travel at the same speed. C equals 3 times 10 to the 8th. So they're all traveling at the same speed. Radio waves are really, really long, so they don't come by very often. Gamma waves are really, really short, so they do come by very often. So if we put these in order from longest to shortest waves, they're already in order from longest to shortest waves. Part B, however, highest to lowest frequencies is the exact reverse, because remember, wavelength and frequency go in opposite directions of one another. And the last one says from least to most energy. And the relationship here is that frequency and energy are going to be direct in this case. So the least energy is radio. And again, as we move from left to right, things are getting more and more energetic. Okay. The same exact things are going to happen to Roy G. Biv, because Roy G. Biv is what I is. So you could replace I with Roy G. Biv. So if you understand that going from left to right, longest, left, longest, we got some memory things there. These are our longest waves. So red is the longest, and it goes to violet, which is the shortest. Same thing on B. It's an inverse relationship. So the highest frequency waves are going to be violet. The lowest frequency is red. So that goes in the opposite direction. And again, least to most energy. Least energy is going to be the ones that have the lowest frequency. Red has the lowest frequency. Therefore, red has the least energy. So again, there's a couple of things going on here. One is understanding the order of these things, and the second part of it is understanding wavelengths, frequencies, and energy, the relationships thereof. You got this question here. It says, what's the relationship between light speed and the index of refraction? I didn't, let me get I meant to have my reference sheet up for this, because it's really just a question about the formula that we have with index of refraction and speed in it. So the relationship between index of refraction and the speed of light is an inverse relationship that we've seen before. So again, in order for n to get bigger, the bottom part of this fraction is going to get smaller. So if the speed of light slows down, in other words, that bottom number gets smaller, then this n is going to end up getting bigger. N to me is kind of like it's almost like a measure of how thick the stuff is that the light is traveling through. So if n is getting bigger and thicker, then it's going to be harder for the light to go through it. Again, another inverse relationship, just like we saw with frequency and wavelength. All right, so let me find my document again. So that's what the answer is for this one. All right, concave mirrors. Let's see if I can make a little sketch here and see if this is how we think about this. Remember, so concave, I always think of is if you're on this side, Concave means it's going to be shaped so that it's like you're going into a cave. Convex would be the opposite. So if we're sketching an image, again, it depends on the reference of the person. So if the person is over here, a concave mirror would look like this. Now, if the person was over here, the mirror is not concave anymore. The mirror will be convex. So if I'm on this side, that's a convex mirror. All right. So what happens with this? Do they bend light together or do they spread them apart? Basically, I'm trying to give you a choice over here. Which one's going to bend light together? The one that's going to bend light together is when they're curved inward like this, because if light hits it, it's going to bounce off and go to the middle. Same thing here. If light hits it, it's going to go off to the middle. This kind of bend, however, if light hits it here, it's going to go upward. And if light hits it here, it's going to go somewhat downward. And they do not bend light together. So that tells us what's going to kind of happen with the light, and then we can get an idea of what would happen to the stuff on there. Now lenses, slightly different, but you can kind of think of the same thing. Something that's concaved is going to have an inward curve. Something that's convex, so if I try to draw this, something that's convex is going to be more like your eyeball, which is shaped more like this. And again, the curvature here is kind of the opposite. So this one, a concave mirror bent light together, but a concave lens, actually when the light goes through, pushes it apart. And a convex lens is kind of, again, like our eyeball, it focuses light. So when it goes through and refracts, it ends up bending downward due to the angles that are on there. So you can hopefully tell from these pictures which ones are bending light together and which ones are spreading them apart from one another. Okay, let's clear these drawings, go down to these things. All right, so ray diagrams. I'm asking where would each of these show up? So we're not really worried about necessarily doing the ray diagrams themselves. However, again, we should kind of have rules. You know, the first one, it's supposed to go to the lens and then through the F. This one's supposed to go through the middle of the lens, and then this one's supposed to go through the F and then straight across. So again, those lenses, excuse me, those rays should give us an idea of where things are, but we should also be able to memorize that if you think of this lens as being like your eyeball, and whatever is back over here is how we see things, when something's further away, it's going to appear smaller. And when things are getting closer to us, they're going to appear bigger. So A is beyond the 2F, which means that A is going to end up showing up somewhere in here, and it should be smaller than it is, and it would be upside down. 2F is where things look exactly the same, except they're going to be upside down. So let me erase that. So if the B is at 2F, then the B should also be at 2F over here. Should be same size. It's hard for me to draw that, but it would also still be upside down. Right. The C, because it's getting closer to us, is going to get bigger, and it's going to end up getting pushed farther back. So it's going to be larger, upside down, and getting pushed farther back. And then the D, again, the D's end up, it's inside the focal length. So it's kind of like when you get something really, really close to your eye, it's blurry and you can't really see it. D is going to be working like a magnifying glass. So if we put an object really, really close to this lens, D would show up somewhere back here. And it's the idea that we would be looking at it from this side to look through. This would be our object, and this would be the image that's going to be made from that. All right. Reminder, the easiest way to tell if it's real or virtual. Real things end up being generally inverted. Virtual things generally end up being upright. Right? So a lens is going to flip everything over except D. That's the only one we're going to get a virtual image that's going to be the right side up. See some similar patterns over here with the mirror. So again, the mirror and the lens do the exact same thing, but they do them on opposite sides, at least with the concave lens. So A is going to be really, really far away. So when A gets reflected and it gets to be made, again, it's going to be small, and it's going to be located between the F and the 2F. The B should, again, the B is at 2F. It's going to reflect back, and it's going to be the same size as it was to start with, and it's going to be at the same place that it is to start with. C, again, we're getting closer to the mirror, so it's going to get magnified more. It's still going to be upside down. It's going to be somewhere back here, and it would be bigger. All right. D is, again, where things kind of start going a little funky. All right, so D is, we're getting our face really, really, really close. This is like when you're popping into a spoon. This is where inside the F, we're going to get a virtual image, and it should be end up being bigger. So you're going to see a bigger version of D on this side of the mirror. Once we get to E, this is kind of like having a convex mirror. So with a convex mirror, this is like the bean sculpture in Chicago. Again, the light rays are bouncing out. So what we end up seeing is we see a virtual image inside of this, and it ends up being a little bit smaller. Again, real ends up being inverted. Virtual things end up being upright. And these patterns are very similar to one another if you can kind of pay attention to them that way. All right, what do we got left? Colors. All right, the easiest way for me to remember how to do all these color things is our first step is making a little chart right here. So I didn't put it, I forgot to write something like this into your paper. So hopefully you're watching this video and you're able to see what's on there. So try to memorize below. If you know your three initials of Roy G. Biv, those are your three primary colors. So we got red, Roy G, and blue. These are the three colors that make up white light. If we mix these things, if we add these things together, we get the secondary colors of light. So red and blue make magenta. Red and green make yellow. Green and blue make cyan, which is our bluish green color. So these are primary colors in the middle, and then magenta, yellow, and cyan are the secondary light colors. And this is where we have to think about, is it light or is it pigment? Because different things happen with them. If we draw some little arrows between these two things, we can kind of start thinking visually a little easier. So we're going to connect these things to show who makes what. So notice we don't connect green with magenta because green's hanging out down here with this. It's a really bad drawing because I'm doing it with my mouse. I apologize for that. So again, what we kind of see is that if I put red and green together, I've got R and G. Where do they end up if we push them together? That turns into yellow. If I do red and blue connect at magenta. Blue and green connect at cyan. Red, green, and blue are going to make white light. Now, cyan and red are also going to make white light. And the reason why is because cyan is made of green and blue, and red, green, and blue make white. So cyan takes two of these colors to put them together. And the same thing happens with the rest of these. So if you do yellow and blue, you're also going to get white because yellow is red and green. So if I do yellow and blue, I'm basically adding all three of these colors together. And the same thing if I do magenta and green. If I do magenta and green, I'm adding the red and blue from magenta to the green and getting white. All right, pigments, you can use this thing again too, that if I add yellow and magenta together, what thing is connected between the yellow and the magenta? It's going to be red. So if I mixed yellow and magenta paint together, I should get red. If I mix yellow and cyan, that connects with green. If I mix M and C, I'm going to get blue. I'm kind of getting out of room here. So again, yellow and cyan is supposed to be green. M and C is supposed to be B. Now, if I mix all three of them, that's where we get black, which is sometimes represented with the letter K. All the colors together are going to make black. All the lights together are going to make white. And the same thing's going to happen with these last three down here. They're all going to make black as well, because if I do cyan and red, right? If I mix cyan and red, I'm mixing all the colors and getting black. If I do yellow, which is, it's going to have these two things in it, and blue, actually I should think of it this way. If I'm mixing yellow, cyan, and magenta, right, I'm going to get black. So if I do yellow and blue, blue has magenta and cyan in it. And if I add that to the yellow, I'm going to get that as well. So you can use this chart, right, to understand hopefully how things fit together. If I get these three lights, I'm going to get white. If I get these three pigments, I'm going to get black. Hopefully not too confusing. All right, last thing. If light does not diffract if it goes into one material to another, that means they should have the same n values, which means they should have the same velocity, which means that they shouldn't change direction. And if they don't change direction, actually, I should have put refract right here. Whoops, not diffract. I should have put refract right here. Again, hopefully you're listening to this and not just turning things in. We should infer that their index of refraction is basically the same, equal to one another, identical. Right? Because again, if the ends are different, that means the light's going to change speed. If the light changes speed, then it's going to not diffract. The light is going to refract when it does that. And that is the last one on there. So hopefully that'll prep you for your test. Talk to me with questions.